Okay, well, welcome to this session. I think you're going to see by the time we get to the end of this session that we are entering a new era for soil fertility management. And so my name is Dale Cook. I am the product lead for the Radicle Agronomics platform here at Precision Planting. I'll be joined in a little bit by Brad Joern. Brad is our soil scientist for the Radicle Agronomics platform. And we're going to be talking about the system that is in use today for soil fertility management and our vision for the future. And so I want to start by taking you to a familiar place. And that is to the farm office, to the kitchen table, wherever your farm team meets and talks about how the year went and what your plans are for the next year. And so I want you to think about the inputs to grow a crop. And it's going to look different wherever you're at. If you're in the Midwest, if you're in the southern US, if you're in Canada, those inputs are going to look different. But in general, your top three are going to be the same. So other than land, your top three are going to be your fertilizer, your seed, and your chemical. And the question I want you to ask yourself is, of those top three, what are you the most confident in? And what are you the least confident in? And why is that? Why is it that some dollars you feel like you're really getting a good return on investment? And other input dollars, it's not quite as clear. You don't have quite as much facts and data to back up the spend that you're making. Which of those is the weakest link in your understanding and your confidence? Well, our journey into soil fertility management started with SmartFirmer. And if I can see a quick show of hands, who here is running SmartFirmer on your planner? Okay, a good number of you. So for those of you who aren't aware, SmartFirmer is a in-furrow sensing device that gives you information both about real-time status of things like furrow moisture, or if I have residue in the furrow, telling me to change my row cleaner settings or increase my depth, but also it's creating a real-time picture of things like organic matter or cation exchange capacity, giving a high-definition view of the field that you're in, such that you could do real-time control from those numbers, or you could use that map to build a recommendation for later date. As we got SmartFirmer out into the market, we started hearing a few things. And one consistent theme that we heard was, I like what you guys are doing, but I want more. I want phosphorus, I want potassium, I want pH. I love these maps. And so we said, okay, we'll look into it. We went back to R&D and we did some research, we crunched some numbers, we looked at the literature, and we came back and we said, you know, great idea, but this is not the right tool for developing a high-density fertility map. But what it did do is it sowed a seed. And it sowed a seed in our minds to say, there is a problem here. And there is a frustration out there in the industry with how we're managing soil nutrients. And what we heard was that part of the pie chart, that part of the input costs is, for many of you, the greatest expense and the least understood. And so it started us on a journey 7 years ago to understand where did we come from in developing the state-of-the-art in soil nutrient management. And so you can see here a picture. We've got a picture from the early 1900s of this finely dressed gentleman out in the field with his suspenders and bow tie, collecting a soil sample that he's then going to take back to a lab, run the soil test on it, and then build a recommendation on that. And so the process is basically the same thing as we've done for the past 80, 100 years. Not much has changed. Now, we also realize that as we look at the three inputs, fertilizer, seed, and chemical, there just hasn't been much investment. There hasn't been much invention in the fertilizer space. We've had probably 1,000 times more dollars put into hybrid development and chemistry development than we've had put into managing our fertilizer dollar better. And so we knew that there was an opportunity there. And so as we started looking at all the pieces of the nutrient management cycle, it starts in the field. It starts in the field with the soil sample. So I'm going to take you on a quick journey on how we get to a recommendation and an application of our fertilizer. And so starting in the field, we go out, got a guy with a soil probe, he's got an ATV, he's running dark to dark. Ideally, he's pulling 12 to 15 cores at every grid that he stops at. In reality, though, it's usually about 4 to 8 cores that actually get pulled. But he's going to stick that probe in the ground anywhere from 1 to 2,000 times a day. He's going to dump the soil in the bag after he mixes it up. He's going to close that bag up. He's going to write on the bag, throw it in the bin, drive to the next zone, and wash, rinse, and repeat all day long, 200, 250 times. He's going to do that. He'll then go back to the shop. He'll box up his samples. He'll drop them off at UPS and ship them off to the lab, at which point, when it arrives at the lab, the soil gets removed from the bag, and then comes a really important step. And the reason it's important is that, in particular, our soil potassium numbers are changed dramatically by this step. And so at this point, the soil gets dried. Depending on the temperature, the time of the drying process, that's going to significantly impact our soil test potassium numbers. And so what you start to see here, as we'll go through the rest of the lab process, is that it is optimized for speed at the expense of accuracy. And it's no wonder. They're trying to drive costs down. They're trying to increase turnaround time such that you can get your soil test results back quicker. So all that makes sense. The next step I want to draw your attention to is after we grind and sieve the soil, we have to get a quantity of soil to do the analysis on. So the whole soil bag, we only measure just a fraction of the soil that you send in that bag. And so we've ground it, we've sieved it, and now we scoop a little bit of that soil out. Now, at first blush, that might seem like it makes sense. You know, when you're making a batch of cookies, you scoop out a 1/4 cup of sugar, whatever, and you level it off, and it seems like you have a uniform measurement. The problem is, in the world of soil, in the world of parts per million phosphorus, truth is determined by measuring by weight the amount of soil. And so the scoop is a simple approximation of weight. Unfortunately, the data would say that by scooping instead of weighing the soil, we can introduce a 40% error in mass. And that's because of the type of soil. So if you have a high organic soil, it's actually going to be less dense. If you have a higher sand content soil, it's going to be more dense. Who's doing the scooping, how they're doing the scooping, all those things change the actual mass of the soil that you end up measuring. We then chemically extract that portion, we filter it, and we analyze it on a machine called an inductively coupled plasma, where essentially we burn the soil filtrate coming out of that step. Now what you'll see on this chart is at many places there are little hands and there's watches, and that indicates wherever you have a human touch or wherever you have a time-sensitive process, those things are shown here. And we'll talk about that a little bit later as we end up talking about the Radicle Lab and how we're eliminating those human touches and the time-sensitive processes. After we complete the soil analysis, the next step is to write a recommendation. Maybe you're doing that yourself. Maybe you have a trusted advisor that's doing that for you. The reality is, the recommendation system that we use today in the US and in almost every other part of the world is antiquated. It's built on data that can be 20, 40, 60, 80 years old. Not only that, but often the data is very generically applied and is not soil type or region specific. Now, after we have a recommendation built, we then have to apply the fertilizer. And here's the ironic part. The ironic part is we have tools to apply fertilizer very accurately in a variable rate prescription. And so whether that's in a modern air boom spreader or whether that's in a strip till rig, we have the tools to apply it accurately. The problem is We don't do a great job of getting the right amount in the right place from a script perspective, from a recommendation perspective. Now, that's the situation. It's slow, it's old, it's inaccurate, but it's the best we've got. It's where we're at. And so, even though it's hard to understand where our fertilizer dollars are going, what the ROI is, it's the best we've got. But this started working in us to say, we've got to do something better. We've got to do something different here. And so, fast forward to a couple years ago, and we had been spending a number of years developing prototypes, developing ideas, developing systems to improve this process. And so what you see here are a number of pictures where we went out and we started getting some feedback. Hey, this is what we're seeing, this is what we're hearing, here's some ideas, what do you guys think? And here's the things we heard. I've waited my entire adult life for something to change in this process, and it's finally here. Or, it's really difficult when I'm sitting down with the customer and writing a recommendation and really having the confidence in the numbers that I'm delivering for the big investment that they're going to make. They said, we really like the control, the efficiency, the accuracy, the vision of what you guys are doing here. And so from those conversations, Radicle Agronomics was born. What is Radicle Agronomics? Radicle Agronomics aims to equip those who are making fertility management decisions. And how do we do that? We've got to start with better tools. Tools that are more efficient, tools that are more precise, tools that aren't making the trade-offs for the sake of speed and time, tools that give you the confidence when you go to spend those input dollars that they're spent in the optimal way. And from those better tools, we expect better data. Data that is accurate, data that is useful, data that is correlated to crop response. And with that better data, we're going to make better decisions. Better decisions as you're sitting at the kitchen table in the farm office with your farm team. Ultimately leading to better ROI, better understanding of where those dollars are going. It's not our intention to replace the experts or to replace you in this process, but to equip you with tools and data and decision support to make sure you're in the right spot with those decisions. So let's take a journey through the Radicle Agronomics system. And it starts by looking at the humble soil bag. And so how many of you have done your own soil sampling before? Let me see a show of hands. Okay, a number of you. Well, we believe that the humble soil bag has had a good run, but it's time to retire. It's really, as you look at it, it's a pretty clunky way to store the soil and the information about it as you write it on the bag or label the bag, fumbling around with opening the bag and pouring the soil in and closing the bag up and writing on the bag. And then there's mistakes like, sloppy handwriting or smudge labels or torn or wet bags. So you drop a bag and it busts open. And so if our goal is to be as efficient and as error-free as possible, we need a new option. GeoTube is what we've developed to replace the soil bag. So GeoTube is a purpose-built, robust, reusable container. This protects the soil sample from spilling from moisture. And so you can see there's a black cap here on the top. And if I'd pass this around, you'd just about tear your fingernails out trying to get this cap open because it is so firmly attached to this tube. In fact, we'll talk about it in a minute, but it takes a machine to take this cap off of the tube. There's a black plunger on the bottom, and the purpose of that plunger is to push out the soil sample and ensure that the walls of this tube are scraped clean such that when we go take another sample with this tube, it's ready and it's not going to contaminate from the previous one. And then the last piece about GeoTube, and perhaps the most important, is on the bottom here we have an RFID tag. And so the RFID tag Its purpose is to store the latitude and the longitude information about the point that the sample was taken from and any other information that is relevant to the soil sample. And so GeoTube ends up being filled on a device that we call GeoPress, and you see that here on the back of this UTV. And so GeoTube is custom designed to work with GeoPress. GeoPress is your assistant in the field. And the idea is we want to make sure that all of the mundane, tedious tasks that you used to do with opening the bag, filling the sample, closing the bag, tagging the bag, all those go away. And so you can see Eli there, he's dumping some soil cores into that little container. He lifts that container up, it grinds the soil, it passes through a grinder and grinds it into that cup. And you can see he'll take that cup and he will then dump it into the funnel. At that point, when he tips the funnel, the GeoPress is gonna stuff that soil into the tube. It's gonna pop the cap onto the tube and it's gonna write all the relevant information to this RFID tag. Again, trying to allow the person in the field to focus on the task that matters the most, and that is getting a quality sample. Here's just an example of the efficiency gains that you can get from the GeoPress. And so this is a side-by-side video of Eli. He's out sampling with the GeoPress there on the left, compared to a traditional way of sampling with soil bags. And so what you're gonna see here is by the time he finishes with the GeoPress in the new process, the traditional process is just getting started on the last zone. And that's consistent with what we've heard from our customers, looking at 20, maybe 30% time savings in the field. Again, focus on eliminating the tedious, error-prone tasks and focusing on efficiency. Now what Eli's gonna do after he's done sampling is he's gonna take crates of GeoTubes back to the shop, back to the office, where he's got a Radicle Lab. He's gonna load up GeoTubes into the Radicle Lab, onto the rack like you see there. He's gonna press the green button, the start button, and he'll then go home for the night while the lab runs unattended. And so Radicle Lab, it's really extraordinary. It's the world's first fully automated soil lab. It doesn't cut corners for the sake of speed. Radicle Lab does everything necessary to ensure that it's going to produce a quality soil test. Human hands don't touch the soil at all. And so we're trying to eliminate any opportunity for error in the soil test. And so this lab, it doesn't need an experienced chemist to run it. It calibrates itself, it checks itself, making sure that it's ready to go and producing a quality result at all times. And so this lab lives in the corner of the machine shed. It's hooked up to 110 power. It's connected to a garden hose to supply water, which, by the way, the water gets purified inside the Radicle Lab. It's got a compressed air source, all for the goal of delivering a maximum accuracy analysis in unbeatable time. Let's take a trip inside the Radicle Lab and see what's going on. So we've got GeoTubes loaded up in the rack. They come up an elevator from the rack. They get read at an RFID reader. The RFID tag gets read. At this point, the sample is checked into the process. It's checked into the process, and all the information, the lat, the long, any other information about that zone is then carried with that soil sample through the lab. After this point of being checked in, we're going to uncap that tube, we're going to eject the soil, and then we're going to wash the tube. And so you can see the uncapping happen there. You're going to see the soil ejection chamber spin around. The soil will get ejected out of the tube. We're going to retract the plunger. The tube will then get washed and ready for the next sample when that tube goes back out to the field. The next step is the soil gets ground. So the soil got ejected into a grinding chamber. You can see here in the video we have green dye just for visualization. But this grinding chamber, its job is to break down the soil aggregates. We want to break down those soil aggregates, blend the soil thoroughly. The goal is that when this soil gets analyzed, we want every soil particle to have access to the chemical extractant to make sure we get an accurate soil analysis as much as possible. The last thing we're going to do here is take out anything that's bigger than a couple millimeters. Any rocks, any residue, any old plot flags, anything else that ended up in that soil sample, we're going to take out. The next step, the soil dumps from the grinder into the ratio control chamber. Now this is a really important part, because what's happening here is we are replacing that 2-gram scoop. And what we're doing here is we have weight and volume sensors that allow us to get a very precise amount of soil, a very precise ratio of water to soil, such that we know exactly how much we're measuring when we get back to the analysis portion of the lab. The other thing to point out is that we blend and mix the whole sample as a slurry. This allows us to get a much more uniform representation of that GeoTube soil that was inside the GeoTube that came to the lab. Let's talk about how the analysis is done. So the soil leaves the ratio control chamber, and it goes to the back of the lab where we do the analysis. The analysis happens with a technology developed at Precision Planting that we call microflow technology. And so what this is pneumatic diaphragm pumps and valves that are embedded inside of an acrylic manifold. The purpose of this is to automate all the steps that typically happen in a lab with the hands of a chemist. We want to take out any sort of possible error introduction that comes from the hands of the soil lab operators. It takes care of itself. It calibrates itself, it checks itself, it diagnoses itself to make sure that it's in spec and producing a quality analysis all day, every day. Just to give you a sense of how accurate microflow technology is, I wanted to give you a little example by showing you this tiny drop of water next to Lincoln's nose. This is half of a microliter. To give you a sense of how small half of a microliter is, it's about 1/1,000,000th of the water that's in this bottle. A tiny, tiny amount. Microflow is accurate within 1/2 of a microliter, or 1/1,000,000th of the water that's in this bottle. At the end of the day, it's about results. And microflow delivers those results through Radicle Lab in record time. From 20 minutes from start to finish, that sample is done. There's 3 samples in progress at any given time. And so that means every 7 minutes, every 8 minutes, we're getting a sample result out. And you can see this lab over here has actually been running the whole time during this presentation. Full tubes going in the front, empty tubes coming out, results being published to the web such that we can write recommendations as soon as that data comes in. The software platform for Radicle is the only purpose-built nutrient management platform out there. And some of the things that Brad is going to talk about in a minute, we're excited to build into this platform to make it and the lab and the GeoPress the future of soil fertility management. And so I'm going to pass it to Brad now. Brad is going to talk about the history of crop response trials and our vision for the next generation.
Thank you, Dale. Good afternoon. Quick show of hands. Who's learning a lot? Winter Conference 2024 so far. All right. You have a broken arm or something? All right, that's better. All right. So when I first met with Dale about 2 years ago, he showed me an early version of the Radicle Lab. And then he shared with me his vision of Radicle Agronomics. And I felt like I was born to be a part of this team. So I quickly accepted his invitation to become part of the Radicle Agronomics team. And for me, this is a bit of a homecoming, because even though I spent 26 years as a professor of agronomy at Purdue University, I was actually born and raised in the ag mecca of Illinois, known as Cook County. Now, for those of you not from Illinois, Cook County is where Chicago is. Okay? So when I was making the trip from Indiana to Illinois, I started thinking about how my life was going to change. For one thing, the whole state of Illinois is on the same time zone. That's not the case in Indiana. So I never had to say, hey, what time is it when I'm talking to somebody in Indiana? And so it's also the central time zone, which is my favorite. I'm also a Chicago Bears fan. And so I no longer was gonna have to pay extra to watch the Bears lose every Sunday, because I'm in Illinois and the Bears are always on TV here. Now, on the flip side, my property taxes tripled. But, you know, we have a fair number of pretty greedy politicians in Illinois. And so oftentimes when they leave office, they generally go to prison. And so I felt like, well, it's just, you know, it's part of living in Illinois. I gotta help us bail ourselves out of debt. But as I was crossing the border from Indiana to Illinois, it occurred to me that even the corn is more greedy in Illinois than it is in Indiana. What I mean by that, if I'm gonna raise a corn, soybean crop, 1,000 acres in Indiana, and I think about the P and K that I'm gonna spend, it's about $130,000. Now, if I wanna raise that exact same corn crop and soybean crop in Illinois, same soil tests, same yield goals, same everything, the fertilizer recommendations in Illinois, they're asking me to spend over $200,000, okay? And so that's what we're gonna talk about today. Why are we here and where do we need to go? Okay, so first, a quick little history lesson about the advances we've made and haven't made in ag technology since World War II. So we start out 1945. There's tractors in 1945, but they're only about 20 horsepower tractors, okay? Now, there is such a thing as a combine, but it's generally for small grains. Now, if you're picking corn in Illinois in 1945, you're probably lucky to have a 2-row corn picker, okay? The soil testing labs were almost exclusively within the confines of the land-grant university because soil testing wasn't mainstream. We were actually starting to develop soil test methods because commercial fertilizers really weren't readily available. You know, for example, the big potash mines in Saskatchewan, Canada weren't discovered until 1943, and they didn't start mining them until 1951, okay? But this is when soil test methods were developed. The ammonium acetate and the 𝗡𝗏 soil tests were both developed and released and published in 1945. So let's jump forward about 40 years to 1984. Well, now we have 150 horsepower tractors. We got rid of the 2-row corn picker and we got combines. And the university labs are shutting down because commercial labs are starting to operate. And these commercial labs are still using the ammonium acetate and 𝗡𝗏 soil test, but the 𝗪𝐿ic-3 soil test method was developed in 1984. Now I realize in other parts of the country, you might use slightly different soil test methods, 𝗪𝐿ic-1, 𝗪𝐿ic-2, the Kelowna in Western Canada, or maybe you're using, you know, modified Morgan or something like that. Well, all of those soil test methods were developed from the 1930s for the Morgan test to 1988 for the Kelowna test. So we are stuck between the 1930s and the 1980s. Let's jump ahead to the present day. Well, now we have 450 horsepower tractors. We have unbelievable combines with yield monitors and moisture monitors, great big corn heads. We can scoop up a lot of corn at one time. We have state-of-the-art laboratories. And we are still using soil test methods from 40 to 80 years ago, okay? So it's not just that our soil test methods are old. Some of the crop response data that we rely on to make fertilizer recommendations, that's also pretty old. I'm gonna pick on Illinois because that's where we are here in Tremont, okay? This is the fertilizer recommendations for potassium in Illinois out of the Illinois Agronomy Handbook. One of my colleagues went to the University of Illinois, has been hunting down the source, the original source of these recommendations, and about a year ago, he shared it with me. He goes, I found it. And he did. And that research was published in 1944 by Roger 𝗏, who developed the 𝗏 soil test. And see that, what a coincidence. Now, the soil tests for the research that was undertaken was in 1935. That's when those soil tests were collected and analyzed. So that means they weren't using the Bray soil test, and they weren't using the ammonium acetate soil test, okay? And the research was conducted from 1938 to 1941. In the late 30s, we didn't even have hybrid corn. Corn was planted in hills, and some of that corn was open pollinated. That's how old some of our crop response data is. Okay, so now that I've destroyed your confidence, let's talk a little bit about why we soil test in the first place. Right? Certainly, we soil test to get a handle on pH, so we can adjust the pH of the soil to optimize it for our crop with lime recommendations. We also want to look at the nutrient status so we can come up with fertilizer recommendations for P and K and micronutrients. Now, one thing you heard in the previous talk with Aaron and Tristan, they're talking about variable rate herbicide applications. Now, the foundational herbicide application that you make is your soil applied residual herbicides. And the rate for those herbicides are based on soil properties, pH, organic matter, cation exchange capacity, and soil texture. I can envision a future state where we can develop variable rate soil applied residual herbicide prescriptions based on the results coming from the Radicle Lab, which is a pretty cool thing. Now, this is a nutrient talk, so let's get back to the nutrients. So when we soil test, the idea is that we pick a soil test extractant that as the soil test level increases, then our yield will increase. And so in the graph that you're looking at, we have soil test phosphorus increasing from left to right on the horizontal axis, and on the vertical axis, we have relative crop yield on a % basis. And so as your soil test increases, so does your yield until it plateaus, and as the soil test increases even further, it doesn't have any impact on yield. And of course, this means no other nutrient is limiting. But in this case, this point at which that yield levels off is about 30 parts per million. Sometimes we refer to that as the critical soil test level, okay? That's an important level because there's kind of two approaches to making fertilizer recommendations. One of them is the buildup and maintenance approach. And in that approach, what we do is we identify the critical level because beyond that, we're not getting an increase in yield. And then the fertilizer recommendation is based on, at any given soil test, how much fertilizer do we need to add to go from wherever we're at to that critical soil test level in some set period of years, okay? And then once we reach that critical soil test level, then we maintain that soil test level with regular fertilizer additions, okay? That's the concept behind the buildup and maintenance approach to making fertilizer recommendations. And that's generally the one that's used in the Midwest USA. Now, there's another fertilizer recommendation system known as the nutrient sufficiency approach. Now, what you do in that approach is after you do your soil test correlation studies, then you do what's called a soil test calibration study. So what we do here is we go out to different fields that have different soil test levels, and then we put different rates of fertilizer on and figure out at any given soil test level, how much fertilizer do I need to add to maximize yield this year? I don't really care about that critical soil test level. I just want to maximize yield, okay? And so in this chart on the right, we have a phosphorus application rate on the horizontal axis, and again, relative crop yield on the vertical axis, okay? So at a low soil test level, in this case 5 parts per million, we level off yield at a 100-pound rate, okay? In that orange curve, where we're at 15 parts per million, we maximize yield at about 50 pound per acre rate. And then in that green one, where we're at 25 parts per million, 20 pounds per acre maximizes yield. Because now we're approaching that soil test critical level of 30 parts per million. So when we're above that, at 35 parts per million, we don't have any fertilizer that we need to apply, okay? So these are the two approaches that are used to make fertilizer recommendations. Now, let's talk a little bit about crop response theory and crop response reality. Crop response theory is this graph. Okay, it's the one that I just showed you about soil test correlation. So all of those little dots are the yield of individual plots or experiments, all right? And so when those dots kind of line up, you can draw a nice smooth curve through there, and it fits most of the data, okay? Well, in theory is the same as reality, but in reality, it's often not, okay? And this is an example. This is a modern crop response trial from Iowa that one of my colleagues, Antonio Mallarino, basically compiled this data set over about 10 or 15 years. Now, it's still, this is soil test potassium, but this is soil test potassium on the horizontal axis and relative grain yield on the vertical axis. That doesn't really fit that nice pretty curve that we see on the left. And so now you're left, the interpretation, beauty is in the eye of the beholder, okay? Because you can get full yield at 100 part per million soil test, or you can get a really low yield at 100 part per million soil test, right? There's a lot of points that go straight up and down from all these different locations. And so when you have messy data, then it really becomes the person who's interpreting the data, and whether they're using the buildup and sufficiency approach or the buildup and maintenance approach or the nutrient sufficiency approach to make their fertilizer recommendations. And so what this means when you throw it all together is fertilizer recommendations are generated by land-grant universities, and every soil fertility specialist is the king of their own little world, okay? And so this is the result. Magic happens at state borders, okay? So what I mean by that is what we see here is a 2-year P&K fertilizer recommendation for 1,000 acres of corn and soybean, where we're growing 175 bushel per acre corn, 60 bushel per acre soybean. P&K are both priced at 50 cents a pound, all right? So everything's the same except the state and the soils that you're working on. So those of you in Illinois like to brag about how much better the soil is in Illinois compared to Indiana. So if that's the case, then why are we putting more fertilizer on to grow the same crop in Illinois as we are in Indiana? I don't know either. It doesn't make sense, okay? Now, if you look at the states on the left over the western part of the north-central US, you can see that the fertilizer recommendations are much lower. That's because those states use a nutrient sufficiency-based approach, whereas Illinois and Indiana use a buildup and maintenance approach. Now, in addition to that, as you go west, the native soil test levels for potassium increase and the availability of that potassium increases. And so that's another reason why the fertilizer recommendations are lower. So the challenge that I see is that soils don't know whether they're in Illinois or Iowa or Indiana, okay? But you can have the same soil in both states and come up with 2 different fertilizer recommendations. And so I think we need to start unraveling a single value for an entire state or a single recommendation system for an entire state that largely ignores differences in soils, and to start incorporating that. Let me show you a quick example. This is how much soils vary. So we only soil sample this top 6 or 8 inches of soil. So these, all of the soils you're gonna see here in this little slide is the state soil for all of the soils, or for all the states that are participating in Winter Conference 2024, okay? So this first group of soils, they're all pretty dark colored soils. Little bit of difference, but you know, nothing that you would really see as that great. But crops don't just grow in the top 6 or 8 inches of soil. They grow down 3, 4, 5 feet. And if we ignore all the differences that we see below where we're soil sampling, we are missing an opportunity to make that jumbled mess of crop response data, start parsing it out by other things so we can get cleaner data sets. Here's another set of soils, okay? They're lighter soils, not too different from each other at the surface, but boy, when you start unveiling what's going on below where we soil sample, that's really different. Here's another pair of soils. They look pretty similar until you start looking at the bottom half, right? And then here's a couple of other misfit soils that don't look anything like it. Now let's look at that entire palette. Soils vary a lot. And it's not just like there's only one soil in Illinois. Every state has about 400 or 500 different soil series, okay? We need to consider that in modern crop response trials. Another thing that's really important is soil moisture. Now, in order for a plant to acquire a nutrient from the soil, the only way for that nutrient to get delivered is through water. Okay, so I have a corn plant here on the left, that little rectangular box. I'm going to show you a little cartoon of the way I see nutrient acquisition by plants. When the soil is saturated, there is no air. There are no air pockets. So a nutrient can jump from a soil particle to a plant root and take a straight line through water. This is awesome for nutrient delivery, but it's really hard on plants because they need oxygen in order to survive, okay? So in reality, what we want is a soil to be moist, okay? Now we have air pockets, the plant's happy, and the soil has enough water film around the soil particles to where that phosphorus ion, in this case, it can't go straight across, it has to follow the water mark to get to the plant root, okay? Now what happens when a soil gets really dry is that now all of a sudden you might have an air gap between soil particles, and now, in this case, all of that soil that's light colored, there's an air gap where those X's are, and so none of that soil can contribute to the nutrition of that plant root because there's an air gap. And so if you think about that, if you're lower in the landscape or you have poorly drained soils, you probably don't need as high of a soil test as you do in the upper part of the landscape where you're shedding water, maybe it's eroded, and you don't have as much water holding capacity. These are also things that should be considered in a modern crop response trial. Okay, I think I've convinced you that we need to revisit crop response trials. Now, this is not a political map. You can tell it's not a political map because the state of Illinois is red, okay? It never really happens. What this is showing you where we have started our crop response trials. The current trials are in red, states in red, and the trials we're gonna start planning for next year are in blue. Our vision is to color the entire US red. Now, we also have planned trials in Alberta, Manitoba, and Ontario. Quick 𝗏𝗏𝗏𝗏 educational opportunity here. Y'all know how Canada got its name. Okay, so the founding fathers really liked the concept of USA. And so what they did, they wanted a 3-letter name for their country too. So they put all of the letters of the alphabet in a hat. And then they pulled the first 3 out, and that was going to be the country's name. And so it was 𝗙𝗲, 𝗛𝗍, 𝗑𝗍, and now you know the rest of the story. Okay, so when we're conducting these trials, we collect a lot of soil because right now we are still tied to the soil test methodology developed 40 to 80 years ago. We don't think those are the best soil test methods for the future. So what we do is we collect additional soil, we vacuum seal it in a moist state, we put it in a freezer for future use. And these soils will be stable for 10 to 30 years, okay? We already have a library of over 50,000 soil samples, and we're just getting started. So when we get a critical mass of crop response trial data, we then can start working on new soil test methods. And when we come up with methods that are better correlated and better calibrated to crop response, you will see those methods being used on the Radicle Lab, okay? And we can do this because We have a state-of-the-art laboratory right here in Tremont, Illinois with 2 full-time chemists, not just soil chemists, but real chemists to help us develop better methods, okay? We also have a greenhouse. And the beauty of the greenhouse is that you can grow crops year-round. And so what we can do there is we can get soils from anywhere and start initiating crop response trials, find out what's the soil test level at which plants grow deficient. And so we just got this up and operating in November. We have a lot of soils that we're working with, and here's an example of a soil that's already phosphorus deficient. So you can see that wheat plant has purple or reddish tips. And then this one is potassium deficient, right? So it's got its leaf margins are turning brown. Okay, these are indicative of nutrient deficiencies. We can also take those soils and add fertilizer to them and then wait for them to kind of equilibrate with the soil and then find out how much fertilizer do you need to add to get, say, a 10 ppm increase in soil test P or K. That's called buffer capacity. Okay? We know that different soils have different buffer capacities, but if you look at the current set of recommendations, all soils are treated the same for the most part. Okay? So we have the tools, the resources, and the experience needed to conduct, analyze, and interpret modern crop response trials so you and your trusted advisor can work together to make the best agronomic decisions for your farm operation. So I want to bring Dale back up so he can explain to you the critical importance that the Radicle Lab plays in this process.
Very good. Thank you, Brad. So I think this is going to make you squirm a little bit, this next session. And so it ought to, but it's one of those things where sometimes truth is uncomfortable. I'm going to share with you a little experiment that we did this last year. And so what this looked like is we took a section of a field. It was an 18-acre field. There was 3 different soil types in this field. And we wanted to figure out if we sampled this field and sent off the soil samples to 4 different places, what would the soil test look like, and what would the recommendation look like that we built off of that soil test. And so we divided this 18-acre patch into 3rd-acre grids. We then sampled those 3rd-acre grids intensively. You can see we even built a custom rig behind that UTV to get a 15-inch width to make sure that we weren't messing with any sort of banding. We weren't overemphasizing one part or another part of the row, but getting an equal distribution of soil from those grids. And so we got 3 sets of 15 cores each. We pulled 2,500 cores out of this little 18-acre patch. And so what we did then is we sent soil to 4 labs. The first lab we sent it to was our own lab, not Radicle Lab, but our own chemistry lab where we do soil tests routinely. And we wanted to have a baseline. And so what we did in our own lab is we used the weighing approach, not the scoop approach, the weighing approach to get the soil measured to analyze. We used the maleic extraction at our own lab, and then the other 3 commercial labs, they of course use their standard process, but also with the maleic extraction. And so let's just step through. We're going to look at the maps that came off this field from the different labs. We're going to look at the min, the max, and the average values. And we're going to start with soil test phosphorus. And so what do we see here? Well, in our lab, we had an average of 17 parts per million, and there's the map. Pretty decent range from your min to your max levels in that field. Lab 1, it looked about the same. Roughly the same min, max, average is almost exactly the same. Lab 2, well, this one's a little bit higher on the average instead of being lower. The map looks approximately the same, right? Lab 3, my map's starting to look a little different. My average, I'm 14 instead of 17, so that's a 20% difference in my phosphorus numbers. That's getting to be a decent difference from one to the next. But the key question is, which one is right? Which one of those labs is right? I'm not here saying it's our own chem lab that's right. Yes, we use the weighing method, but I'm not here saying that one's right. I'm not sure. Let's look at potassium. Again, with our own lab, 121 parts per million. Lab 1, oh man, things are starting to look pretty different. The map, I'm not sure if I could have told you that map was from the same field. My average, I'm at 82 instead of 121. Lab 2, well, lab 2 is actually closer to our own lab, 107, so maybe a 15% difference. And then we get to lab 3. Lab 3 looks nothing like the other labs. In fact, the highest soil in lab 3 at 80 parts per million is lower than the lowest soil from lab 2. But I can't stand here today and tell you that lab 3 is bad. So which one is right? Which lab is giving us the accurate analysis? Let's look at the impact of this on the pocketbook. And so we built a 2-year rec from the Illinois Agronomy Handbook with the assumptions you see there. And so with our own lab, we were looking at $230 an acre for the P and the K. Lab 1, $296, so $65 more an acre. Lab 2, it's pretty close to the baseline, $16 an acre more. And then lab 3, we were $95 an acre more just because of the lab that we chose to run the soil at. But still, which one is right? If lab 3 is right, I'd rather invest the dollars to make sure I get the yield back. Let's take a look at this. So let's imagine plotting those 3 labs on a bullseye. And this isn't a quantitative chart, but just to imagine. In general, labs, at least within a time window, are relatively repeatable, relatively consistent. Lab 1, lab 2, lab 3. The question is how do you define accuracy? How do you know which one is going to give you the right number to build a recommendation off of? Now, the truth is, it's kind of a trick question. Because lab 4, which I didn't talk about, is actually the lab that's right. Is actually the lab that's accurate. The unfortunate reality, though, is that lab 4 doesn't exist anymore. You see, lab 4 was the soil lab at the university that ran the crop response trials and analyzed the soil from the crop response trials. And that's how you define truth in soil testing, is you have to marry the lab results with the crop response data. They have to go together. Otherwise, we're stuck with 4 different charts from 4 different labs and we don't know which one's right. And so, for a truly accurate soil test, we need 2 things. First, we need a repeatable lab, consistent day-to-day, week-to-week, year-to-year. And we are doing that with Radicle Lab by taking out the human touches, and every Radicle Lab is a clone of the next. And so whether it's in Idaho, whether it's in Alabama, whether it's in Eastern Europe, in Ukraine, this lab is going to be producing the same results. The second thing we need is crop response data built off of soil tests from that lab. And as Brad shared, we are building that database of crop response data from around the country and soon to be from around the world. And so let's wrap up and talk about how we see the future of soil fertility management. Number 1, I hope it's clear to you, it's certainly clear to us, that we see a huge opportunity to improve the way we manage soil fertility. Number 2, we believe that fertilizer crop response data must be tied to a lab in order to be truly useful. Number 3, as Brad laid out, it's a lot more complex. It's a lot more sophisticated than just a soil test number and a yield goal. And that's the direction we need to go as an industry to really get this dialed in. And last but not least, our aim is to equip your team to optimize your fertilizer dollar. And so whether that's at the farm table or the farm office, we want your team and your trusted advisors to have the tools, to have the data, such that ultimately you can make the decisions to optimize your fertilizer dollar. Last but not least, Radicle Agronomics, we're new, and we want to stay connected to you and keep you informed about the direction we're going. And so snap this QR tag here, and it's going to take you to a really quick form where you can put in your information and stay up to date with the latest news from Radicle. And so we look forward to sharing with you in years to come where we're going, and just want to thank you for your attention and participation today. Thank you.